Just a second. By the way, can you hear me?
Yes.
Yeah.
Oh, okay, thanks. Okay. So good afternoon, everyone. So this is the first live session for the first phase 1 obstacle avoidance robot. So today we're basically going to talk about this week's challenge. However, we first are going to refresh our knowledge just to like be on the same step. Then we are going to discuss the TinkerCAD challenge. And finally, we're going to talk about the obstacle avoidance robot challenge. So without any further ado, let's talk about theory. So I think 2 weeks ago, the first batch of asynchronous material was released. So from that asynchronous material, you should have been more familiarized with the Arduino programming and general electronics. But just to remind you with some programming basics. So void setup, basically all Arduino code can be divided into 2 parts. So there is void setup part. So basically in this part, you set up all variables, all sensors, all motors, and that kind of stuff. And one thing which is important to remember is that it only runs once. Then under the void setup part, there is void loop part. And basically it is the code which repeats multiple times and usually want your sensory measurements to take place in that part, as well as like other stuff. In addition, to define objects, you should define pins. So to define pins and objects, you use define function. So you write define, then the name you assign to that object and the pin you connect to that object. Or you can create an integer value, for example. So you say integer, the name of your object and the pin. In addition, you can control your pins in 2 ways. So you can assign the pin mode. So basically what pin mode means is that you take this pin or the variable you assign to the object, and you say that this pin acts as an output device or input device. And this is quite quite self-explanatory, since output devices are logically devices that does not take input, sensory input from the environment, while the input devices does that. And to control your pins, you use digital write function. So it functions like this. So you write digital write, you write the name of your pin and you assign a state. So there are basically 2 types of states. There is low and there is high. So as you write low, you turn off the device, and as you write high, you turn, oh no, as you write low, you turn off the device, and as you write high, you turn on the device. In addition, there are some more specific functions which are more related to specific objects. So for example, related to server, there are a servo function. So basically it is used to define the servo object. So you write servo, then the name of your object, which, for example, in the later examples, we are going to use basically my servo variable. Then there is the name of the servo write function. So basically, it is used for the servo position control. So as you can see here, you write the name of the servo, you write right, and in the brackets you insert the angle of the servo. And finally, related to ultrasonic sensors, there is a pulse in function. So this function basically measures the duration of the signal. So yeah.
Just a question, please.
Yes, you can.
For the servo, when specifying the angle, is it between 0 and 180 or negative 90 and 90?
It is, well, to be
Or it
honest,
depends on the type of servo you're
yeah,
using?
it mainly depends on the type of servo. Since, like, for example, well, at least like the servo which was specified in our kits has like spread of 180, but other servos can have like spread of 360 and so on. So it basically depends on the servo, but the majority of servos usually have the like the spread between the 0 and 180.
Okay, thank you.
You're welcome. Yeah. So for this week, you had a challenge. So you had to construct an obstacle avoidance robot that stops whenever there is an obstacle nearer than 30 centimeters. And as it stops, it has to check the distance from the nearest object on the right and left, and then choose the path with the largest measurement. So basically, as it was mentioned at the beginning of the series, we're going to support both learners with and without physical kits. So first, let's start with the non-physical challenge. So for this, we used TinkerCAD circuit simulator, and last week we released the circuit part, the circuit part of the challenge, which you can see on the left, and on the right you can see the motor, the L293D pinout. So without any further ado, let's go straight into TinkerCAD simulator. So let me just open. Yeah, I think. Okay. Yep. So here's our circuit. So let me just a little bit explain it. So basically, this circuit is used to simulate the behavior that would happen in real life if we would use like real robot. So we can imagine that the upper part is the left motor and the lower part is the right motor. So like the bot is a bit shifted by 90 degrees, if you understand what I'm saying. So basically what we want to achieve using this simulation is that we want the motors to spin until we trigger this ultrasonic sensor by putting a virtual obstacle nearer than 30 centimeters. Then after the ultrasonic sensor is triggered, we basically want to turn the server to, I think it is said, yeah, so first to the left. So we're going to use my servo right uh, about 30 degrees function, and then we want to turn our servo to the right. And as we turn to both of these angles, we want to measure our distance and then choose the direction with the largest distance. So to help to visualize it, we're going to use LEDs. So basically, we are going to say that as the so-called bot is going forward, both LEDs are turned on, and whenever there is an obstacle, both of LEDs should turn off. Then the servo is going to turn to the left, right, measure both distances, compare them, and if, for example, the left distance is larger than the right distance, we are going to turn on the left LED, which is right here, and vice versa. So yeah. Also, I think I've covered. Well, I think we can like go straight deep into code. So just for the time being, I wrote some of the functions. I'm going to explain everything, and there are some gaps for me to write. So yeah. So first, as it is always with Arduino, we first define our libraries. So as we aren't going to use any like external libraries as it is going to be the case with PhysicalBot, which I'm going to explain a bit later, I'm going to use only the Servo H library. So after including this library, we first define the pins. So here you can see the definition of the motor pins. So we define the positive and negative pins, as well as the speed control pin. So although during the asynchronous material, you were not presented with the L293D with this driver pinout, if you would look at it, just a second. Yeah, so you would see that like, let me just check. Yeah, so basically you see those pins which are name enabled. So these pins are mainly responsible for controlling the speed of the motor. So basically in this line, as well as in this line, we define these speed control pins. Then we have to define the trig and echo pins of the ultrasonic sensor. So if we see in the circuit, the trig pin is connected to analog input 0. So let's define it. While the echo pin is connected to analog input 1. Then we have to define the servo pin. So as we can see, these are the ground and the power pins, which are connected like quite self-explanatory to the ground and power, while the signal pin is connected to the digital pin 2. So let's write that. And finally, we're going to finish off with the LEDs. So for the LEDs, for the left LED, which is this upper LED, we use digital pin 13, write that. And for the lower right pin, we use digital pin 12. So as well, let's complete that. So it's all with the pin definitions. Then we move on to do some variable definitions. So first off, we defined maximum speed just for the simplicity and for more control. So for the maximum speed, well, basically the speed can go from 0 to 240, if I'm not mistaken. So we choose this like quite safe option of 160, which we actually are also going to choose in the real-time settings, since we don't want our motors to spin at the maximum speed, just for the safety of our bot. Then we define our duration, centimeter, and distance variables. Well, I'm going to explain them a bit later. Then we use the earlier mentioned servo function, and using our include servo library, we define our servo object, which we name myServo. Then we define the collision distance, which according to the problem is 30 centimeters. And we define the left and right distance. Then,
just a question: why
yeah.
why are the left and right distance integers, not doubles or long? Because maybe the ultrasonic, for example, it will give me 27.5. So isn't it better if I take doubles for these values?
Well, it mainly depends how much accuracy do you want, since, well, if we analyze like the real setting, like as you construct the real robot, it usually isn't so much accuracy. Since, for example, well, at least in my code, like for the forward function, I had to change the maximum speed of one side and add 10 to it, since it was like shifting a bit to the right. So it isn't like, as motors aren't spinning so accurately, there isn't a very huge difference between whether or not we are going to use like double or integer values. But of course, you are correct saying that we could have used double, and it is probably more in case if when you want more accurate device. But in this case,
Okay.
well, both suitable. Yeah, yeah. Uh, and then moving on, here we have our setup bar. So as I mentioned earlier, there is a place. It is a place where you set up all your pins, all your sensors, all your motors, and so on and so forth. So first of all, let's set up our motor pins. So quite logically, all our motors are output devices. So let's just write that. Yeah, in just a second. Okay, so our speed control pins are output devices, but for the digital write function, we want to assign a value. So as I mentioned, speed motor pins in our case is going to be responsible for the speed control of the motors. And also we said that our maximum speed is going to be 160. So let's write it that our speed motors are assigned a value of max speed. Okay. Moving on to the motor pins. So all of them are output devices. So let's also write that. It's going to be a bit quicker. Okay. Then for the ultrasonic sensor part, as we mentioned, ultrasonic sensor has basically two like these sensory pins. So there is a trig pin and echo pin. The trig pin is mainly responsible for sending the signal, while the echo pin is responsible for receiving the signal. And like from this wording, we can guess that the trig pin is going to act as the output device, while the echo pin is going to receive signal, thus it is going to be the input device. And for the LEDs, both of them are output devices. Okay. Also, in addition to that, like as we start our robot, well, like for example, with this physical robot, okay, I could accidentally turn the servo, like for example, at this way, and in this way, if I don't make sure that the servo is facing directly, I could like go on and the servo would perceive this a bit shifted direction as the 90 degrees direction. And this could have caused some problems at the initial state. Of course, like later on, it is going to be a bit corrected, since we're going to say like to position it at 90 degrees, but at the first it would go this way and there might be problems. So thus at the setup bar, you also have to say that our servo is facing directly. So we write servo write 90 function. And for the attach, which is basically saying, well, in the brackets, we say the number of the pin our server is connected to. So as we can see, it is pin 2. Thus, we write attach 2. Okay. And also, just for the safety, we want our robot to wait in place for 2 seconds. So thus we write delay function. Okay, and now let's move on to the main part. So in the loop, which is going to be repeated over and over, we first write 90 degrees. Of course, you can say now that why are we doing this as we already did this in the setup bar? And as we know, setup order is the first function that is going to be ran, but it is going to be a bit clearer as we go through. So let's just say my server will write 90. Then after waiting 0.1 second, we basically want to finally measure the distance, the forward distance. And for this, we are going to use measure function, which we are going to discuss a bit later. And basically, as I said, that if this measured distance is less than our defined collision distance, then we want our robot to make a decision. So this is programmed in this part. So we say that if the distance that is going to be measured using this function is less than collision distance, which is 30 centimeters, then we want to turn off our LEDs. So in other words, digital write LEDs low, and same goes with the write pin. And we want to make a decision, or in other words, use the change path function we are going to discuss also a bit later. However, if our distance is more than collision distance, we don't want to make like any decisions. So we simply go forward. We delay 0.1 millisecond and we turn on our LEDs. So thus we write, okay, so we used quite a lot of functions which we haven't covered. So let's cover them. So first off, the forward function. So for the motors to go forward, one of the pins has to be low and one of the pins has to be high. Yeah, so to go forward, we say that motor pin 1 is high, motor pin 2 is low. So these pins are corresponding to the upper pin, to the upper motor. And for the lower motor, we also say that motor pin 3 is high and motor pin 4 is low. So here's our forward function. Also, it is quite logical that as we face some sort of obstacle, we want our robot to stop. Thus, it of course is quite useful to write a stop function. So basically, what a stop function, well, for robot to stop, we want to turn off all the motors. So self-explanatory, we want all of them to be at low state. So let's write that. Then it is also logical, as we mentioned before, we check the distance at the right and at the left. So logically, if we want to change our path accordingly, we want to have left and right functions. So for this, well, basically, as you think about it, as you're going forward, all your motors are spinning in the same direction. So for example, it is all spinning like this way. However, as we're only using 2 motors and not like 4 motors, we have to think, how are we going to turn left or right? So for example, okay, so our motors are spinning like, okay, this upper direction. So for example, I want to turn into that direction. So basically, I have to keep spinning this motor up while I have to change the direction of the other motor. So as this motor is going up and this motor is going down, the robot is going to turn to that direction. So basically, to go to left, we want this motor, just to clarify, yep. So we basically want this motor, which is the upper motor, to go, yeah, we want, okay, I made here a mistake. So we basically want this motor, which corresponds to the upper motor, to go to the to down, or in other words, we want to reverse it to to reverse it, we reverse these values. So here we write low instead of high, and here we write high instead of low. While we don't want to change anything according to this motor, so we leave high and low. And similarly, the same logic goes with the right direction. So we don't want to reverse this upper pin, this upper motor, when it keeps spinning upper. So we keep our high and low values. On the other hand, we want our lower motor to change its spin direction. Thus, we reverse it, and instead of high-low, we write low-high. Okay, so here are our driving functions. So now let's talk about decision making. So as we write here, we are using change path function. So basically, what it means, as we say, when to stop. Then we want to turn our servo to the left, then measure the distance. Then we want our servo to turn to the right, measure the distance, and then make the decision. So first, we use the stop function. Then we turn to the left. And here you can note that we're saying that we're using the 30 degrees. And you may question, why are we using 30 degrees and not like 0 degrees, which would correspond to the left? And honestly, it's basically due to some safety, since like from the practical perspective, it doesn't make a huge difference if we measure the distance at 30 degrees or 0 degrees. However, it provides us with some sort of safety factor, since in many cases, servos can actually churn more than expected. So, for example, if you experiment with real robot, you may see how you say to servo that it has to, like for example, position itself at 150 degrees, but instead it's positioned itself to 180 degrees. And for example, if that servo only can like churn from 1 to 180, it can basically break your servo. So this is why we're using 30. Also, as we turn to this, we use a measure function. Write it. Then we have to wait for 1 second. Then we turn 150 degrees. And we also use measure function. And then we want our servo to come back to the initial 90 degrees position, just to make sure that we're going straight forward later on. And we want our robot to compare those distances. So for this, we're going to use a separate function. So in this separate function, we compare the left distance, which we measure here, with right distance. And if the right distance is greater, we basically want to turn to the right. So thus, we're going to use right function. Also, as we said, we want to, just a second, we want our LED to indicate that we are turning right, since we are in the virtual environment. Thus, we are going to use digital right function. And we're going to say that, just a second, right LED, yeah, its name, right LED is turned on. So therefore high. Then we want to wait 2 seconds. And then we want to turn off our right LED. As later on, we are going to as we go forward, we are going to turn on both of our LEDs, and there's no point of like the remaining turned on right LED. So we write digital right LED low. Similarly, for if our left distance is greater or equal to the right distance, we turn left, so left, and we turn on our left LED. So here we use digital right left LED high function. We also wait 2 seconds and we turn off our LED. So we write low. Okay, and finally, we came to our measure function. So to measure, well, let's just think. What are we going to do as we measure? So first off, we are going to send the signal from the trick pin. Therefore, we're saying that we are using digital write function, and we're saying that digital write our trick pin has to be turned on, or in well, actually no. First off, we want our trick pin to be low, since we have to make sure that our trick pin is not triggered from the last function. Thus, we first have to turn it low, just to make sure that it is turned off. Then we have to do it. We have to wait for 5 milliseconds. It doesn't particularly have to be 5 milliseconds. It can be like any number. However, it doesn't have to be like very large number, since we don't want our robot to wait like purposely. Then we want our digital pin, trick pin, to be outputting signal. So we use digital write trick pin high. Then we want to delay for another 10 milliseconds. It can be like any number. It just be quite small number. Then we want to turn off our trick pin. And simultaneously, without waiting any further, we want to record this time measurement. Thus, we use pulse in function, which basically measures the time the echo pin is triggered, and it assigns this value, which is in milliseconds, to the duration variable. Yeah. However, we're not so actually focused on the duration, since we want distance and not like the time. Therefore, we have to convert this time to distance. So at first, it is quite logical that as we measure the distance, it is double the distance, since it goes to the obstacle and comes back. So we first have to divide it by 2. Then we have to divide by 29.1. And what this number means, it basically we here have time, and we want the distance in centimeters. So what we basically are doing, we are dividing the time by the pace of sound in air. And the space is calculated by dividing 1 by the speed of sound in air. And thus we get the value of 29.1. And we say that like the main purpose of this function is to return the centimeter value. So basically, if I didn't make any mistakes, here is our function. So let's just simulate it. It can be quite slow, but let's just see. So as you can see, our motor is turned on at 90 degrees, as we expected. Then to simulate the obstacle, we press on the ultrasonic sensor. As we see, the current measurement is 125. Thus, we want to lower it to less than 30. So for example, 25, it turns to right. Yeah, it's quite slow. It then turns to the left. It also measures the distance. And it chooses the left path. as you can see, like, for example, as it turned to the right, the measured distance was about 25 as we moved this object. And as it turned to the left, I moved this object to 90 centimeters. Thus, it chose the left, and thus the left LED was turned on. Okay, so let's give another try. So for example, okay, also 25 LEDs are turned off. It measures this distance, which is 25. Then for this, we use 20. And as you see, it shows the right distance as it is larger. So here's our TinkerCAD function. Okay, so now let's come back to our presentation. So now let's talk about the physical bot challenge. So first off, let's talk about the connections. So let me exit the full screen mode. So basically, as we're using the motor shield, the connections are a lot easier than in the motor driver. So basically plug onto the Arduino or motor shield. We connect our servos to these holes. Then we connect our power supply to the power supply section. Then we connect our motors to these motor pins. And then for the sensory part, we connect our trig and echo pins to the analog section, and we power it to 5 volts and GND section. So now let's talk about how it is going to look in Arduino IDE. Okay, so here I have my Arduino IDE function. So basically, this time we aren't going to make everything manually. We're going to use some sort of functions and libraries additional. So first off, we also are going to use, as in previous example, servo library. However, this time we're also going to use the motor library, AF motor library, which is specific to our used motor shield. So thus we include AF motor library as well as NewPink library, which supports ultrasonic sensors. Then we, as previous time, we define our pins, our maximum distance, maximum speed, collision distance, and so on and so forth. Then we have to create our sonar object, which is part of NewPink library. So we write NewPink sonar. And as variables, we use trig pin, echo pin, and maximum distance. For the choice of maximum distance, it isn't very important. It just has to be like in logical boundaries. It doesn't need to be higher than 5 meters, since it is unlogical, since most of the ultrasonic sensors only function in about 4 meters range. So we thus use 350. Then we are going to create our motor objects. So for this, we are going to use a FDC motor function, and we're going to create motor 1 object, which we're going to assign to the first pin. And for the other motor, we are also going to read this process, but this time it is motor 2 and pin 2. Then, as in the previous example, we're going to use servo function. So servo, my servo. Then we define our variables, and in the step part, we use attach function. So this is new function. We use it in previous examples, so never mind. So we basically say that our servo is connected to the 10 pin, and we also make sure that our servo is facing forward. So on the loop section, it's basically quite the same logic. So we measure our distance, and we measure our distance with our custom read sensor function. And if we check if the distance is less than collision distance, and if it is the case, we change our path. Otherwise, we go forward. And for this, we're going to use move forward function, yeah. And I'm going to want to wait a little bit. So then we define our functions. So for the stop function, the AF motor library has specific keywords. So to turn off the motor, we use release function. Just a second. So we set both motors to release. To move forward, we set our motors to yeah, we set our motors to forward. And we set our speed to the maximum speed, which is 160. Then to turn left, we want our left motor to go backwards while the right motor is turning forward. So thus we write motor 1, motor 2, which is right forward, and motor 1, which is left backward. And we also use maximum speed variable. To turn right. Okay. To turn right, we want our left motor to turn forward while the right motor is turning backward. So we use motor 1 forward, maximum speed, while the right motor is turning backward, also at the maximum speed. And in our change path function, we basically first want to stop, so move stop. We want our servo to turn 30 degrees. So here's my servo byte 30 degrees. We want to wait for a half second. Then we want to measure our distance, and we measure our distance using read sensor function. So read sensor. Okay, then we want our servo to turn 150. So we write 150. We want to wait a little bit, and we also want to measure our distance with read sensor function. Then we want to wait a bit, and we want to come back to the initial position. And quite logically, we want to compare both left and right distances. So we use the comparison function. And in this function, we basically say that if the left distance is less than right distance, then we want to turn right. And to turn right, we use turn right function. Turn right. And if the left distance is greater or equal to the right distance, we use turn left function. Then we have to talk about the read sensor function. So basically, we're using the custom function which belongs to the new ping library. So it is sonar ping. It basically functions in a similar manner as the previous pulse in function. It basically returns the value in milliseconds. So we assign this measurement to yes variable. And to convert this variable to centimeters, we have to divide it by a specific function which is called US round trip CM. And basically it turns this time measurement to centimeters. However, we have to talk about another case. So for example, as we go forward, And for example, we define that our maximum distance at which our sensor functions is 350. But for example, if the obstacle is 5 meters apart, well, if the obstacle is 5 meters apart, our trick pin is going to send the function, is going to send the sound signal. However, our echo signal is not going to receive that signal, and it's going to perceive it as 0 signal. So thus we have to think about this case, since like, for example, if the obstacle is 5 meters apart, our robot should go forward, but if it returns the 0 value, which is illogical, it is going to stop and like check distances to the left and right, which is not logical as the nearest object is 5 meters apart. Thus, we have to make sure that if our value is equal to 0, it shouldn't be equal to 0. And we say that, like, for example, this variable is 300 and not 0. And we return our centimeters value. So here's our code for this. Just for the simplicity, I recorded previously the demonstration part. So for the demonstration, as you can see, the robot is stern and it's making decisions. However, one thing to note. Okay, so which is quite important as we talk about the ultrasonic sensors. So I think it's this part, no, a bit earlier. So as the robot is approaching this plant, you can see that it basically, it doesn't stop near the plant as it stops near the box, which is the main disadvantage of ultrasonic sensors, as they struggle a lot with some unusual substances. So for example, they might find it difficult to stop at the plants, they might find it difficult to stop at the cloth, and so on and so forth. So ultrasonic sensors are only useful if we want to measure the distance from quite structured objects. Okay. So far, do you have any questions? Okay. I think I can continue. So here was our, okay. So here was our part for the phase 1 challenge. And later on this day, in about an hour, there's going to be a phase 2 material release, and also next week, next Monday to be particular, we're going to have a live session for this asynchronous material. So the topic for the phase 2 is maze solving robots. So as the name suggests, we're going to construct maze solving robots. In this part, however, the asynchronous, like online part, is not going to be carried on a TinkerCAD simulator. We're going to use Robot Benchmark website, which is based on the Weebot software, which we are going to be implementing in the further lessons. But yeah, so we are going to release the phase 2 material in about an hour or so. And here it is. So thank you very much, and see you next time. Or if you have like any questions related to this week's material or like the trolls in general, we can ask. Or if you don't want to ask these questions now, you can write it to Discord. I'm going to answer them. So yeah.
Thank you very much.
Thank you.
Thank you.
Bye.
Bye.
Thank you.